Hello, my name is Matthew Balcer, and welcome to my presentation on the multidual sensitivity method in ray tracing transport simulations. I want to thank Los Alamos for hosting the virtual student symposium, allowing me to showcase my work that I did in my internship over the summer with Los Alamos. So again, my name is Matthew Balcer, and I'm currently a PhD student at the University of Texas at San Antonio. And over the summer, I worked with Dr. Jeffrey Favorite on the multidual sensitivity method implementation in a ray tracing transport simulation. So first, I'll go over how we can obtain derivatives using multidual numbers. Then I'll go over the simulation in which I implemented the code in, which is a ray tracing transport simulation. And then I'll discuss the process of how this method can be implemented in code. And then I'll present some numerical results that verify this method. And then finally, the conclusion. So we can obtain derivative expressions by through the Taylor series expansion of a function f of x with a step applied to the variable of interest. And this gives us the function itself plus the higher order terms, which are of the form a derivative times the step. So we have the second derivative times the step squared, and so on. So if we apply this step in the real domain, we can obtain finite difference approximation, which leads to subtractive cancellation errors and also truncation errors. But if we apply the step in a non-real direction, we can alleviate this subtraction cancellation error. So applying this step in a non-real direction, we use a dual number, which I denote as epsilon, where a dual number is defined under the constraint that epsilon squared is equal to 0. So applying this non-real step to the variable of interest x with a step size h, which is a real number, the Taylor series becomes this equation, which since epsilon squared is equal to 0, all these higher order terms go to 0, they drop out, and we're left with a Taylor series expansion that truncates exactly at the first order derivative. So all we have to do is solve for this first order derivative, and we can obtain our expression. So we do this by taking the non-real part of either side, so all of the terms with an epsilon as the coefficient, taking the real part of these terms. So this term will drop out. And then divide by your step size h gives us an expression for the derivative. So all we have to do is add the non-real step to the variable of interest x, evaluate this function, take the real part of the terms with a coefficient that has epsilon, and then divide by step size. And we get a first derivative with machine accuracy. So Fike and Alonso extended this to obtain second order derivatives by applying a step in two separate non-real directions, which using dual numbers we denote as epsilon 2 as the first non-real direction and epsilon 1 as the first non-real direction and epsilon 2 as the second non-real direction. These are known as multi-dual numbers, which are defined under this constraint, which is epsilon squared is equal to 0, epsilon 2 squared is equal to 0. Epsilon 1 times epsilon 2 itself is not equal to 0, but this quantity squared is equal to 0. So applying these two non-real steps to x gives a Taylor series expansion that truncates exactly at the second order derivative, since these higher terms are 0, so these higher order terms drop out. So expanding this, simplifying, and then solving for a second order derivative gives us this expression where we apply the steps in two non-real directions, evaluate the function, and then take the real values of the terms that have the coefficient of epsilon 1 times epsilon 2, and then divide this by your step size that you took, and you get a second derivative with machine accuracy. So this is extended to arbitrary order partial derivatives uh, of a function with any number of variables. So all you do is apply the non-real step to your variables of interest in different non-real directions, evaluate this function, and then extract all the real parts of the terms that have this epsilon 1 times epsilon 2 times dot 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 times epsilon n coefficient, and then divide by the step sizes you took. So now I'm going to go over the simulation in which I implemented the multi-dual differentiation method in. So Dr. Jeff Favorite has developed a ray tracing code that calculates the leakage of uncollided particles, assuming that there's no scattering. So this is done by placing a detector point on the outer surface of the material, emitting a ray through the material, and analytically solving the flux, which is this equation here. This is the flux. And then repeating this multiple times and then numerically integrating over all these rays to get the leakage. So currently they have implemented the adjoint base derivative method to get first and second order partial derivatives of leakage with respect to isotopic parameters, and also they have first order derivatives with respect to surface locations. However, they want higher order derivatives to help to get better estimates for uncertainty quantification problems as well as optimization problems. So that's a great fit for this multi-dual method. So how this multi-dual differentiation method is implemented in a code. So first we need a multi-dual library which handles all the algebraic operations. Luckily, the lab at UTSA has developed a library to do that. It's called MultiZ, and in your source code, we define the variables of interest as multi-dual, and then define all the functions that use these variables as multi-dual as well. If a variable or function is an array, we have to alter the syntax slightly to match what the multi-dual library calls for, but no new formulation, it's just a syntax change. And then write a few lines to extract the derivatives. So the real part will just be your function evaluation, and then you need to extract the non-real parts to get your derivatives. So for running the code, you add those non-real steps to your variables of interest, run the code, and then your output will be the real part is your function evaluation. Your first non-real part is your first derivative, and then that epsilon 1 times epsilon 2 part is your second derivative, and so on. So we applied this to a two-region sphere, and we got back all the multi-dual sensitivities matched within about 2 to the negative 10% of existing adjoint-based derivatives. So in general, they match up through 10 to 12 digits, matching the existing adjoint-based derivatives. So we can also get new derivatives that have yet to be obtained by the adjoint method, which are derivatives with respect to surface location. And so we compare this with central differencing, and we got very good agreement. They match through 4 or 5 digits. And these results have been published in the American Nuclear Society conference this winter for 2020. And we are also now currently working on a journal publication for this. So in conclusion, we successfully implemented the multi-dual differentiation method in a ray tracing transport code to obtain arbitrary order derivatives of leakage with respect to isotopic parameters and surface locations. So we've showed that this multi-dual differentiation method can be applied in the nuclear engineering field. And so I'd like to acknowledge the Connect program, who this is funded through, and also Dr. Jeffrey Favorite for being my mentor throughout this internship with LANL, as well as my advisor, Dr. Harry Millwater, who provided really great insight on this project. So thank you.